I'll show you that there is an interesting and cute connection to SDPs and matrix factorization, which will be the key component of our main result. So I also want to preface that this is joint work with Meena, who's a grad student at UC Berkeley and the primary driver of this work, and Ilya, who was a colleague of mine in MSR, but now is involved in an independent startup. Okay, so jumping right into the problems setting for today's problem. So we'll be focusing on learning prediction function, where the data consists of inputs denoted as X and labels denoted as Y. And the goal is to learn a function which maps input to something from which we can infer Y from. And specifically, we'll be focusing on a class of functions which are parameterized by a set of tunable parameters we will denote as W throughout. And I'll try to be as consistent. I've tried to be as consistent with the notation as possible. So you can just think of W as the weights of a neural network to just have one example in mind. Or if you're more familiar with linear models, it's just weights, coefficients of the linear model. And a natural way to select a function, such a function which will be good for prediction, is to minimize some kind of loss over observed examples. So if you have like some set of observed input label pairs, you minimize the loss. You find a parameter that minimizes the loss over the observed examples, and that is your candidate prediction function. And if you have lots of data compared to the number of examples, this is a well-defined problem, and you have standard analysis which shows that you get good prediction. But today we'll be focusing on the class of problems known as overparameterized models. Although I'll not define it precisely, or it's not super rigorous definition, we'll work with the notion that it's a class of functions, it's a class of problems where the function class we are considering, or the set of parameterized function class considering, it's so large that the training loss I previously mentioned, which is minimizing the loss over the observed examples, has multiple global minimizers. So in other words, there are multiple functions which perfectly fit the observed data, and more importantly, not all of them are good predictors for new examples. So in particular, this has to be a setting where just minimizing the loss doesn't give you good performance on new examples. And specifically, we care about the setting because this is indeed very common in the practice of deep neural networks, where it is common to train very large networks on very large scale data sets. And usually, like, the loss minimization involves some kind of gradient descent over the parameters. And this is indeed a classical picture of like overfitting we see in many machine learning classes, where you can think of very large neural networks representing set of all continuous functions. And if you have a small set of data points compared to the size of the function class, then you have many functions which perfectly fit the training data, like I've shown in the toy example here with like 4 data points. And you can imagine that most of these functions, most continuous functions which fit the toy data will not do well on new data points from any reasonable distributions. So in some sense, to learn anything meaningful here, you need some kind of a capacity control. So you need to restrict the space of functions somehow. You can either, traditionally this was done by explicitly adding a regularization, where you say how you want to restrict the function class. And more recently in deep learning, it is also common to have regularization implicitly by the optimization. So even though the optimization objective itself has like very ill posed, the specific algorithms you use, specifically variance of gradient descent, which is common in neural networks, explores only a small trajectory. It has a very specific update rule, and hence it explores only a small region of the entire function space. So there is an implicit constraining of the function space going on when we just minimize this with any algorithm. So this has been studied, like the notion of implicit regularization and also how it interacts with other notions of explicit regularization has been studied in the neural network. Today we'll look at a slightly related but complementary problem to that. In particular, the notion of among the ways to control the capacity or restrict the model class, the notion of norm-based capacity control is very popular. It has long been argued that restricting the magnitude of the weights rather than restricting the number of weights or restricting the size of the function class explicitly plays an important role in learning, in going back even to 90s. And in the modern, this holds true even to the modern day, where the modern practice of deep learning, it's common to have both explicit and implicit regularization, which have been implications in terms of restricting the norm of weights. In particular, the L2 norm of weight appears prominently in many recent research. I just wanted to add a clarification here, is that this talk is not meant to convey that L2 norm of the weight is the only measure of complexity we should care about. In fact, like in some of the important problems, it has been shown that non-L2 norm or even non-norm based capacity control can happen with implicit regularization. But we will be focusing on L2 regularization, not because it's the only thing which is important, but it is an important measure of complexity. So setting the question for today, so the question we ask is like, we have the set of parameters and then we have the set of functions which are mapped by this parameter. So you can think of this capital F as a mapping from the parameter space to function space, and the script F is the set of all functions in the function space. And the question we ask is like, if I put a restriction in the parameter space with something simple like something as simple as an L2 norm ball, so we restrict the functions, the parameters to an L2 norm ball, what does the resulting capacity control in the function space look like? And you can imagine from this control that this obviously depends upon how this capital F is defined. And this capital F is essentially given by different architectures, different parameterizations, and so on. And we'll see a specific example of how drastically different answers you get depending upon F. And but more generally, for any parameterized class, we can capture this notion of the function space inductive bias by this induced regularizer. So we can define an induced regularizer, which is essentially the representation cost of realizing a function in terms of L2 norm of weights. So mathematically, for every function in the function space, you define this complexity measure, which is essentially like the minimum L2 norm of weights required to realize that function. So you have an architecture which realizes many functions, and among all the ways you can realize a specific function, you pick the one which minimizes the L2 norm of weight. And you can see that this in some sense captures the real inductive bias when you minimize L2 norm of parameters, because if you think of any minimization where you regularize with L2 norm, so along with some loss over the outputs of the model, then that is exactly equivalent to minimizing this R induced regularizer measure subject to the same loss. And so in that sense, it exactly captures the real inductive bias. So the another interesting thing about this is like now we can study this inductive bias as a purely representation cost and not worry about like the implicit regularization, explicit regularization, and so on. So in some sense, we have bifurcated the problem where on one part, we study what is the nature of the implicit regularization in the parameter space or explicit regularization in the parameter space. And then once we know the nature of regularization in the parameter space, we can study its effect in the function space as a separate abstraction. And today we'll be looking at that kind of an abstraction specifically for L2 norm. So there has been some previous results which directly or indirectly answer this question for some simple networks. And one of the most illustrative examples is this case for linear networks, which I find it very interesting because it's somewhat surprising if you're seeing this for the first time. So the idea is you have a regular neural network, but I remove all non-linearities. So essentially, it is just very complicated way of representing a linear model. So you can think of now a fully connected network, which in the end represents a linear function, and the function is represented by essentially multiplying a bunch of matrices together. So it's a linear model which is just represented by matrix, 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 vector multiplication. It's just a different parameterization of a linear model. And the other parameterization is using a convolution. And specifically, if you have a full dimensional convolution, that is convolution where the kernel size is same as the input size, you can again represent any linear function as a convolutional network followed by a linear layer. Here again, we are still representing the same class of all linear functions. In both the cases, we are the set of functions represented by these networks is just set of all linear functions. And we can ask what happens if we do L2 norm regularization on these two different parameterizations. So we are doing L2 norm regularization on the weights, not on the end-to-end function. And we get very different answers. To begin with, like for fully connected network, the induced regularizer in the function space, which in case is linear models, is just the L2 norm of the linear function, linear model. On the other hand, for full dimensional convolutional network, you can show that it's a much more complicated and interesting inductive bias, where you take the Fourier representation, discrete Fourier transform of the end-to-end linear model, and do an LP regularization where P is 2 by L, and L denotes the number of layers. So for example, for 2-layer networks, this is an L1 norm in the Fourier space. So this is a fundamentally different inductive bias that compared to just fully connected networks, even though these two function classes are exactly like the same, and we are still doing L2 norm in the parameters. And then in the second case, it's also interesting that something simple like an L2 norm in the parameter space gives us something complicated, even non-norm, like for L greater than 2, it's a quasi-norm. You get an induced regularizer, which is much more interesting and much more complicated to understand. So in today's main result, I'll be discussing some of the extensions for convolutional network. But just for completeness, there is also other problems where it's easy to get from the literature the exact nature of the inductive bias. And two important and interesting problems are matrix factorization, where if you represent a matrix as a product of two full dimensional factors, then the induced regularizer is essentially a nuclear norm. This you can also get simply from like the variational characterization of nuclear norm. And somewhat more interestingly, if you think of 2-layer networks with infinite width and ReLU activation, so this is the first nonlinear network with specifying. If you think of ReLU networks with infinite width in the second layer, then you can show that for a single one-dimensional input, so it's a scalar function. The induced regularizer can be given in terms of something related to the total variation norm. So here again, we see that something very simple in the function space, parameter space, leads to something more interesting and complicated in the function space. So for the rest of today's talk, I'll be looking at, I'll be showing what does this induced regularizer look for linear convolution networks specifically, and how it depends upon the kernel size and the number of channels. So this will be building on our previous result on full dimensional kernels with one single channel. Here we'll be showing what happens if you have multiple channels and different kernel sizes. So, that was pretty much a very long setup of the problem. If there are any questions I can take now before I move on to the main results. Okay. So going on to the main result. So I'll set up this problem a little starting from the beginning. So consider 2-layer convolution networks. So what is with linear activation? What exactly does it look like? So you have an input X, and then you take a convolution with a filter U. So U here is part of the tunable parameters. So you take a convolution with a linear filter, with a filter U, and then you take a linear combination of them, the outputs of the filter. So there is no nonlinearity. So the effective end-to-end function is still a linear prediction. And the set of parameters are essentially U and V. All of these are trainable parameters. And the question is, what is the induced regularizer in the space of linear predictors when we minimize L2 norm of U and V? So for the simple case, you can write down what the end-to-end linear predictor is. You can write with a little bit of algebraic manipulation, you can show that the end-to-end linear predictor is essentially convolution of U times some reversal of V. So you can just think of as U times V. Although this by itself is looks a little bit complicated, as many of you from the list I can see that have a more electrical engineering background, it's easy to see that this is a much simpler representations in the Fourier domain. So if you look at the same network in the Fourier domain where we take everything in the Fourier space, then you can show that it looks like a much simpler network, which is call it diagonal network, because it's like the linear layer is just diagonal and everything else is zero. And here the idea is you have like just diagonal connection between the inputs and the first layer, and then you just take a linear network. So this is a much simpler representation of the same network. And in particular, from the point of view of implicit regularization, you can show that any trajectory on the first network is equivalent to a gradient descent trajectory on the second network. So it doesn't change any of our analysis for both explicit or implicit regularization. And now it's easy to see that at least if we don't have a restriction on U, if U is unrestricted to be a d-dimensional if it was a d-dimensional kernel, then the Fourier transform of U, which is just the discrete Fourier transform of U, is pretty much unrestricted. And you can see that when k equal to d, where the kernel size is equal to d, you exactly get the Fourier transform of beta L1 norm. And you can pretty much see that with one inequality where so the L2 norm of the parameters is the same as the L2 norm of the Fourier space, at least when we normalize the Fourier transform. And you just need the product of U hat and V hat to be beta, and you can obtain this by setting U hat and V hat to be square root of beta while absorbing the sign in one of them. And since both U hat and V hat are unconstrained, you can indeed do that. And with this one inequality, we can easily see that you do get a full L1 norm in the Fourier space. But but what happens when we don't have when we do have restrictions on U hat? So in other words, if the kernel size is small, like small, then we cannot realize all possible U hats. In particular, we may not be able to realize square root of beta hat. And in this case, I apologize, I didn't mention one of the notations here, where any Z hat is essentially just a Fourier transform of Z, or U hat is a Fourier transform of U, and so on. And beta hat is the Fourier transform of beta. So going back to the small kernel size, we can see that in the extreme case of k equal to 1. So if you have a kernel size of just 1D convolution, which is not very commonly used, then you can see that U hat is restricted to just a scalar multiplied by an all ones vector. So now this is a much restricted space of U hat, and you cannot get minimum L1 norm. In fact, in this case, you can show that the induced regularizer is some scaling of L2 norm of beta. So now we see a difference not just in when you employ different architectures like fully connected versus convolution, but also within the same architecture class, if we have different hyperparameters, we again get very different inductive biases. Specifically, in the case of two-dimensional two-layer convolutional network, you see that depending upon the kernel size, you get very different inductive biases going from L2 norm to L1 norm in the Fourier space. So in particular, L2 norm is basis independent. It doesn't have to be specifically Fourier space, whereas L1 norm is something very specific to Fourier transforms, which makes sense from an image processing perspective. And in fact, you can try to see this you can try to see if you can get closed form solutions for general K. And we found that in general, it is hard because even for K equal to 2, the end-to-end function is a very complicated expression in terms of like the Fourier transform. So we in general do not hope to get a closed form solution for general case of K, the kernel size K. But experimentally, what we observe is that as we increase the kernel size, we start to get more sparsity in the frequency domain. So just before I go to the next slide, I wanted to explain the figures here. So the top figures are, this is a model trained on an MNIST dataset, where the top figures are what we obtain when we do kernel size of K equal to 1, and the top left is what you get for kernel size K equal to 1. Top right is the Fourier representation of that particular predictor. So on the left hand side is the signal space representation. On the right hand side is the Fourier space representation. And the bottom row represents what happens if you have kernel size of K equal to D. And you can, even in this cartoon pictures, you can see that like the second picture is somewhat more useful from an image processing perspective because it encodes some notion of translation invariance. This is specifically for the classification task of separating 1 and 0s. And whereas for K equal to 0, you're just looking for something which looks like 1 in the center. Whereas for K equal to D, you get somewhat more translation invariance. And now we can actually do the experiments, at least for more general case. And what we observe is like some notion of group sparsity coming in for intermediate case. So you go from K equal to 1, 5, 16, and 28, going from top to bottom, left to right. And here again is the signal space and Fourier space representation. And we see that as we increase K, you get more and more sparsity in the Fourier space. and which in turn translates to like some notion of translation invariance qualitatively. Okay, so we, as I said, it is unlike, we found it very hard to get a closed form solution for general K, but we wanted to see if there is a more interesting representation for general K. And this is where we notice that there is an SDP relaxation which can be of interest. So specifically, if you look at this objective for a general K, you have minimizing U hat square, V hat square, subject to beta hat being the product of element-wise product of U hat and V hat. And now if you look at both the objective and the constraints, you can see that you can write it as the objective can be written as trace of UU transpose and trace of VV transpose. And the constraint can be written as some linear function of UV transpose. This naturally suggests that you can look at the optimization over a lifted space where you create the space W obtained by stacking UV and then its transpose. So you create this K plus D by K plus D rank 1 matrix, UU transpose, which has all the components we require to represent both objective and the constraint. So, so in some sense, the RK of beta can be exactly written in the lifted space as trace of W subject to some linear constraints and a rank constraint. So this now starts looking like an SDP with a rank constraint, and a natural SDP relaxation is when we drop the rank constraint, right? So we have so we started with a single two-layer convolutional network, and then we showed that like there is a natural SDP relaxation which you can obtain by just dropping the rank constraint for any kernel size. And once we observe this, we can also generalize this slightly better. So now you can think of what happens for if you have multiple channels. So in a convolutional network, if you have multiple channels, you're essentially in the second layer, you're repeating what I did multiple times. So you have a set of multiple kernels, which we now denote it as capital U, each of size K, and number of channels is denoted as C out, capital C out. So you create multiple convolution outputs, and then you take a linear combination of all the final outputs. And we see that with the same kind of algebraic manipulations, you can write the constraint essentially as a diagonal of U hat V hat transpose. And if you do the same process we did for the SDP relaxation for one channel case, we get the same SDP, but now with a rank constraint where the constraint is essentially C out. So where the constraint is essentially C out, and here again we can get a SDP relaxation by just dropping the rank constraint. Now just staring at this equation, we can see that when number of channels, output channels is greater than like say K plus D. K plus D is the size of the network, size of the matrix W. So if the number of output channels is greater than K plus D, then you get an exact tightness. This is just by looking at the two equations here, because if C out is greater than K plus D, the rank constraint is in some sense irrelevant. With a slightly more modification, if we actually go down and look at the KKT conditions of this SDP, you can show that if C out is simply greater than number of kernels K, if C out is greater than K, then we have SDP tightness. So in some sense, these two are equal as long as C out is greater than K. That is not so obvious to see, but it's not very difficult if we do write down the KKT conditions. But even more surprisingly, what we actually show is that this SDP relaxation is indeed tight for every value of C out. So for any C out, like the induced regularizer is indeed independent of C out and is given by a convex function which can be written as an SDP. And in particular, this also means that the induced regularizer for this two-layer convolution is a norm, and which based on our previous results shows that it interpolates between an L2 norm when K equal to 1 and L1 norm when K equal to 2. In fact, we can derive like bounds on when it is closer to L2 norm, for what values of K it is closer to L2 norm, and for what values of K it is closer to L1 norm, and so on. So this gives us a little bit more handle on how to handle, how to handle the inductive bias for small kernel sizes. But most importantly, it tells us a very interesting testable hypothesis that for two-layer networks, the number of output channels doesn't matter. at least from this inductive bias perspective. And in fact, like although this is derived for like explicitly regularizing L2 norm of parameters, we can create a hypothesis that gradient descent, which we suspect minimizes L2 norm of the parameters, also has this property. And in fact, we test this hypothesis experimentally, where for different number of channels, and we run simply gradient descent. We don't do explicit regularization with L2 norm, but we run gradient descent and look at the predictors obtained. So the top left set of figures are for k, different values of k, and c equal to 1. And we also show the plots for c equal to 2 and c equal to 4. As we see in all three cases, the visually like the parameters, the learned prediction functions, which are implicitly regularized by gradient descent, indeed follow this hypothesis that they are independent of number of channel sizes. In fact, we can also test it explicitly in like even though this was just a visual representation, the same thing can also be seen in terms of the values, that across different channels, you see very little variance in the induced bias. And what is even more interesting is that as an experimental hypothesis, this can now be tested even on nonlinear networks. And although we have not done extensive experiments across multiple data sets, in at least the small MNIST data set, we observe that even when we add ReLU nonlinearity and add biases, which we didn't talk about like in the theory sense, the hypothesis of that the learned predictor or the complexity measure of the learned predictor is independent of the number of channels also seems to hold for ReLU nonlinearity. And this is something which is very exciting because we started on a theory for a very simple object, and then we have a testable hypothesis which we seem to be hold true for like even nonlinear networks. And this is something we are exploring further more experimentally. Just to give a little bit of an idea of the proof technique, because I thought this was a very quick connection in the proof technique. So like I mentioned earlier, if we just look at the SDP, KKT conditions of the SDP, we can easily show that all the solutions of the SDP are of rank at most k. And hence, as long as the C out is greater than k, the rank constraint becomes irrelevant, because an optimum of the SDP can be realized, any optimum of the SDP can be realized with that rank constraint. So now showing tightness for C out equal to between 1 and k is much more trickier. And in fact, like the way we show it is by showing that, so there are solutions of SDP which are not rank 1, but we show that for any such solution, you can implicitly construct a rank 1 solution which achieves the same objective and satisfies the constraint. And that part of the proof is, as far as we know, is also an interesting contribution of this work, because we couldn't find any reference to the proof. And it's also an interesting proof technique because of the way we implicitly construct the rank 1 solution and not explicitly provide what the rank 1 solution is. And one of the key lemma, which I don't know if anyone here has seen it before, is which we also find is that if there are A and B in R par K, and we take a d-dimensional convolution. So essentially, we pad it with d minus k zeros and take convolutions of the equations of the form A convolved with A and B convolved with B. For any such summation, there exists a single C of the same size k, which can be written, which can capture the summation. And like we did an extensive search and we couldn't find a proof to this, but we thought this result is of independent interest beyond this paper and beyond like the SDP tightness itself. So, so this was our main result for multi-channel linear convolutional network. In fact, so one of the shortcomings of this work is, like two of the shortcomings of this work is that it only deals with 2 layers. So at this point, we don't know what happens if we have multiple layers. So does the number of output channels, which is the width, starts mattering? Presumably yes, because the number of output channels becomes the input channel for the next layer. So that is a problem which we continue to work on, and I actually don't know what is the answer to it. But the other question is, we don't deal with like inputs which are multiple channel. What happens if you have multiple channel inputs, which is very common in image processing where you have RGB color channels. And in this case, like we can again try to do a similar SDP relaxation. So, but we do study this, but there are some gaps in the study. So just to very briefly say this, I won't be able to do justice to this problem because even just introducing the notation is going to be like take a while. But roughly, this is a case where it's a similar setup with multiple output channels, but now you have also multiple input channels. So you can think of the inputs as a matrix rather than a vector. Just to clarify, this is not a matrix of images. So it's a matrix across channels. So the images itself can be handled in the previous, one channel image itself can be handled in the previous setup. So here again, one of the interesting things is like, can we say similar things about the number of output channels? And the immediate answer is no, because even with a very basic analysis, we can show a lemma saying that multiple output channels might be required to even realize all possible inputs, all possible linear predictors. So here the linear predictors are a set of matrices, and even to simply realize all the matrices, you might need multiple output channels. And specifically, the number of output channel greater than number of input channel is a sufficient condition for realizing all the functions. And with similar SDP relaxation, we can we conjecture that is also sufficient to show the SDP tightness. We can create a similar SDP relaxation, and we conjecture that it is also sufficient to show SDP tightness, but we haven't shown that part yet. But two special cases where we do get interesting results and concrete answers are again for k equal to 1 and d, which I thought was very interesting to present. Is for k equal to 1, if you remember previously, like the solution we got was like the L2 norm of the predictor. So we got something which is basis independent and also an RKHS norm. On the other hand, if you have multiple inputs, then you get a solution which is the nuclear norm of the end-to-end predictor. So here it's not a matrix factorization problem. It is a convolutional network. But once you have multiple inputs on the end-to-end linear predictor, you do get a nuclear norm regularization, which is again basis independent. It doesn't have to do anything with Fourier transform or any special basis for computer vision. But it's interesting that it is not an RKHS norm, and it tries to do the tries to have low rank across channels, low rank representation across channels. And even more interesting scenario is when k equal to d. So this is the case of full dimensional convolution, where for single convolution, we obtained L1 norm in the Fourier space. For a single channel, we obtained L1 norm in the Fourier space. And for multiple channels, we obtain something like a group sparsity in the Fourier space. So you get L2 over the channels and L1 over the Fourier dimension. So this again is an interesting inductive bias where you still want sparsity across the frequency spectrum, but you try to capture the same quantities across the color spectrum, which is like the channel spectrum, if I were to qualitatively put for computer vision applications. So, just to summarize, I mainly talked about single input channels, but our work itself covers both single input and multiple channels. And summarize the main result, a key contribution of our work is to show that for single input channel, the induced regularizer is indeed independent of number of output channels. And from this, we can infer a lot of other things in terms of the nature of the inductive bias as being interpolating between L2 and L1 norm. And we also get a hypothesis which we can explicitly test in the experiments. For multiple input channels, I didn't really go into details, just wanted to give the main results. Here again, here in contrast to single input, we show that multiple output channels may be necessary even to realize our model. But for large enough models, number of output channels, we again show that it can be captured by an SDP, and after a point, the number of output channels stops mattering. And that's again a hypothesis. Although I didn't present experiments, we do have experiments on the updated version of the paper, which should be out shortly. That's all I have to say for today. Thank you for your attention.
Great, Suriya. Thank you very much for a very nice talk. Do we have any questions or comments? I have a question, so let me break the ice.
Yes.
Can you go back to your, I mean, this question that you had on A plus A star? Yeah, that. So that star is, it's, sorry, you had it, yeah.
Yeah.
Is it supposed to be a circular convolution?
Sorry?
Is it circular convolution?
It is a circular convolution. Sorry, I should have mentioned it. Everything I talked about is for circular convolutions.
Okay. Yeah, I think this statement is essentially the fact that if you have a trigonometric polynomial that's non-negative, then it's actually the square of something, right?
Yeah. So we do actually, the proof does goes through the polynomial representation. We did look into that literature, but it's I didn't find exactly this result, but it is. Yeah, I actually was going to reach out to you because you're the expert on this topic.
I mean, I think yeah, probably other people like Hugo. I don't know if he's still here, but yeah. So this so I think again in the if it's really the circular stuff and this statement is about essentially because really it applies to, I mean, on the left hand side you can have an arbitrary sum, right? Because then you could reduce it
because you can recursively
turn.
apply the same.
Yeah, exactly. So the statement is really somehow that whenever you have something that's on negative, it's a single square. And in the trigonometric case, that's really like the sum of two squares in the real case. So,
right. So the
which
thing,
is
showing that this holds for real values was also the tricky part, because in some sense the left hand side is a palindrome. If you write it in a polynomial formulation, it is a palindromic formulation. So the roots are paired. But to show that the right hand side is represented by a real times real is the more tricky part. So showing that if C was allowed to be complex, this is not. We found some results which show that. But to show that C is real, you need to argue about the multiplicity of like norm 1 roots.
I see.
Roots with absolute value. You have to show that they have even multiplicity.
I see.
And that specifically looks at this. It's not just a palindromic polynomial, but it's a palindromic polynomial of the type A of x times A of 1 by x plus B of x times B of 1 by x.
I see.
And so that there is a little bit of, it's not just from the palindromic polynomial.
Great, thank you.
Yeah.
Any other questions or comments? You have a question in there from Christian. Christian, do you want to ask this directly or should I paraphrase?
Sure. So if I understood correctly, everything here is for 1D convolutions?
Yes, but it can be converted into 2D convolutions by like similar way. You can look at the 2D Fourier transform. I mean, I believe most of the results here can be converted for 2D convolutions. Is that your question? Yeah.
I was just wondering whether anything can fail. If we consider 2D convolution.
So we did, I mean, the SGP becomes much less intuitive because you are, in some sense, it is still like a linear function in the 2D space, 2D Fourier space. But it just becomes super messy to describe even like specify the notation. But qualitatively, so we did check that like everything here translates to 2D convolutions, but the proof and the paper is written for 1D convolution.